warm welcome to Bill Crowe.
Hi, everybody. I'd like to talk tonight about the magical smartphone and what makes it that way. Right? What would someone say in the 1950s if they saw one of us standing out there playing with our cell phones? Right? Our smartphones are a wonder. Some people might even say they're a magical device. To produce them require a confluence of many different innovations. What follows is an overview of many of the advantages and innovations that have been needed to make the smartphone possible. First of all, I call smartphones, or phones, the phones we carry with us, they're kind of disruptors. They have replaced all of the devices you see on the screen there. You see a boombox, you see a video recorder, you see a tape recorder, you see a little handheld radio, you see a mixer, a keyboard, a calculator, DVDs, videotapes, tapes, weather radios. It has replaced amplifiers. It has replaced all of those things with one of these. And you carry it around with you every day. It has disrupted. I'll just go down through a brief list, and I'll bet you could, if I had a smaller class, I'd say, gee, let's go through and what do you think it's affected? The boombox, the tape recorder, the camera, the video camera, the radio, CD players, VCRs. These are businesses that are now out of business because of our cell phones, primarily, right? Record players, flashlights. It even put a crimp in the flashlight industry, right? Calculators, address books, GPS systems. I have one. I think I just put it in the scrap heap, right? TVs, right? The post office, right? How many emails do you know? How much personal mail do you get in that mailbox? Not very much. The phone, the natural phone you have on your wall, the watch. The current generation of younger folks don't even own watches, except when Apple came out with one, then they had to get one. A compass, your phone can be a compass, right? It's your calendar. Some of us are starting to use it as our wallet or our credit card, right? It's a notebook. Clock, timer, alarm every night. I say, wake me up tomorrow, Siri, at 7 o'clock, and she's very helpful, right? Weather forecast, books and dictionary. How do you spell panache or pithy? Games, newspapers, right? You don't need a newspaper anymore. You can look it up on your phone or your iPad. A musical tuner. I have a tuner on my device. I use to tune. I make Native American flutes, and I use it to tune the Native American flutes. It's the translator. The latest Apple operating system came with a Translate app. So it has disrupted all those industries, right? So what are the advances it took to have this little small package in front of us, right? Well, it took some innovations in the radio frequencies. We had to get authorization and figure out how to use different radio frequencies. How to use, or it required the development of large computers, because of what we do on our phone requires a big computer in the sky somewhere. Large capacity data storage. We're talking not megabytes or terabytes. We're talking much, much bigger capacity there. Screen technology has to get better, so we have a clearer picture, right? And one called semiconductor development. Somebody asked me what semiconductor meant. Semiconductor is basically sand that they refine, and the reason they call it a semiconductor, it doesn't favor a positive or negative charge. So it's a great base for much of the industry much of the technology that goes into making our devices, our phones. Speaker development. How did we get not one, but two speakers in our phone, right? Camera development, battery development, speech recognition, fingerprint and facial recognition, right? LED light and light sensors. All of this is in that little package you carry around with you. So what I'd like to do this evening is just talk about a few of these things and give you a little more background about them and how they came about, right? Internet development. Well, what is the internet? The internet is the lines that go around the world and connect us all together, right? And that's why it's called the internet. But what's that different than the World Wide Web? Well, we had all the lines connecting everybody, but nobody had a common technique, if you will, to use to communicate. And that's where the World Wide Web comes in. A set of standards of communications came about, right, in 1989 that said, hey, we're going to use this particular technique and we're going to call it the World Wide Web, right? The internet is enabler, it's the wires, and the web is what causes it to be able to work, okay? Internet's the connector, the web is the controller. And if you look at that, that's what the internet looks like around the world. And this is what the www, World Wide Web, right? It's the connector, http://www, that's in front of all our web searches that we don't have to put in anymore. But that's what controls everything. Your phone, for example, has many different antennas to communicate, right? It has GPS antennas. It has cell phone antennas to connect to cell phone towers. By the way, GPS is low Earth orbit satellites. It has Wi-Fi. Wireless fidelity is what Wi-Fi stands for, in case anybody was wondering, right? And that's to communicate to something that's within 100 feet of you. Then we have Bluetooth. That's to communicate to something that's in 10 to 30 feet of you, right? We use that. Well, we use the Wi-Fi for our home networks, or Panera's restaurant. The Bluetooth we use to communicate, for example, to our car stereo systems, or headphones or speakers, or a couple. And there's one more that they've added to the iPhones. Recently, they've had them in Androids a little longer. It's called NFC antennas, or near field communications. They're within about a foot. And that's what you use to show your cell phone at one of these places where you usually put your credit card. Many of them now have the capability to just flash your cell phone in front of it, and it will take the money out of your credit card. Of course, it has to have your password or your fingerprint or your facial recognition in order to do it. So if somebody got your phone, they couldn't use it. As far as the speed of the internet goes, it's gone from 1G, 2G, 3G, 4G, and 5G. Now that doesn't mean that 5G is 5 times better than 1G. And let me show you the comparison there. And it shows you the years. 1G was in 1980 and 5G is in 2020 is when we'll start seeing it more robust use. 5G is reaching speeds that are 20 times faster than 4G, right? So if we look at the comparison there, 3G, 4G, 5G, And those are the years, right? The bandwidth, or the size of the river, or the cable, or the conduit getting places is called bandwidth. It was 2 megabytes, then 200, and now it's going to be greater than 1 gigabyte per second. Latency, you may have heard that term, you may not have. Latency is the amount of time between when you tap the screen and you get a response, right? And if there's nothing interfering, like the internet's down, or the website's busy, or your Wi-Fi isn't working well, if nothing's in the way, it used to be between 100 and 500, or 1/10 or half a second, right? Then it got to 20 to 30 milliseconds, and it's going to be less than 10. So the responsiveness of your device, assuming nothing else is going wrong, is going to get quicker. The average speed was 144 kilobytes, then it went to 20 to 25 megabytes. And with 5G, it's going to be 10 to 20 times, with 10 to 200 to 400 million bytes per second. Okay, so that's pretty well what's happening with antennas and communicating outside your device. Once you communicate outside your device, you have something called large computers have to be around. Why do large computers have to be around, right? Well, guess what? When you do a search on Google, Bing, Yahoo, or DuckDuckGo, right? For example, Google alone processes over 3.5 billion searches per day. That takes some kind of compute power somewhere in the cloud somewhere, right? Speech recognition, just think about this a minute. You say, Siri, what time is it? And to do that, Siri had the computer hardware between you and your answer has to say, okay, I've got to change that sine wave of a voice into some kind of words. And then I have to push those words over to a computer that analyzes the words. And then another place that figures out how to answer that, convert it back to the voice of Siri and play it back to you. A lot of those transactions take the cloud. And when you get the cloud involved, just think about what's going on there. You push the button and it usually responds very quickly. By the way, that's the new symbol for Siri. There's 157 million homes in the United States that have some kind of smart speaker in them. Email. How many emails are processed by folks these days, right? 246 billion emails per day are sent, have been sent by the end, were sent by the end of 2019. That's 246,000 million emails every day. The stock market. Big computer in the sky is needed for that because it processes 58 million stock trades. That's not individual stocks, that's a trade every day. Streaming videos and music in places like YouTube and Pandora. There's the different symbols of the different streaming capabilities, right? When you're streaming, by the way, what that is you're actually hooked to a cloud somewhere and it's real time sending you and playing the information to you. It's not necessarily being saved on your device. So you have to be hooked to a cloud somewhere to be streaming. 300 hours of video are uploaded to YouTube every minute of every day. Almost 5 billion videos are watched on YouTube every single day. Just think about that, right? And now we're having facial recognition, right? And the FBI does facial recognition on folks and is able to identify with their database. We'll have a little bit more on that a little later, but you get the idea there, folks? It takes a lot of compute power to be able to do that. And it goes megabyte, gigabyte, terabyte, petabyte, exabyte, and zettabyte. And each one of these is 1,000 times greater than the previous one. So tera is 1,000 gigabyte, et cetera, et cetera, et cetera. For example, the Maps application, just think about that. It uses millions of pictures taken from space, stitches them all together, combined with street level images at Google that is collected with thousands of vehicles traveling around the world. And it stitches them all together and shows them to you. We take all this for granted, right? Google Images gives us billions of images at our fingertips. I don't know if you've ever used Google Images, but it's phenomenal if you need a picture of something, right? Email providers have mass storage facilities to house all your email. The email that you sent doesn't go directly to you, it goes to some cloud first. And it stays in that cloud until you delete it, right? Cloud storage, where we can put documents. And I know the club uses Dropbox, for example, right? All right, large computers. Display and touch, right? We have these display screens, right? There are two technologies combined in one. The quality and crispness of the display and the ability to touch the screen and make it do something, right? So I'm going to talk a little bit about the screen, the touch screen. And this is a video. And Yui, could you turn on your speaker and let me know if you hear it? Can you hear
Touch
it?
screens are everywhere, not just in smartphones,
Yes.
but in supermarkets,
Thank you.
ATMs, and even airplane seats. And you may have noticed that not all touch screens are the same. The old school touch screens can be pretty tough to use. Sometimes it feels more like a push really hard screen instead of a touch screen. On the other hand, certain smartphones and computer monitors are really responsive to many different touch patterns. There are lots of different technologies out there, but they're all trying to achieve the same goal, sending precise electrical signals from specific locations on the screen. One of the most widely used types is resistive touchscreen, where you have to physically push and bend the screen to make it work. Resistive touchscreens are made of two separate layers. The top layer is made from a flexible, transparent material, such as polyethylene, which is a common plastic used to make things like soda bottles. And the bottom layer is made of something more rigid, like a sheet of glass. To make the screen work, both of these layers are thinly coated with some sort of metal compound that conducts electricity, like indium tin oxide, which is commonly used because it's transparent. These layers are also separated by tiny insulating dots called spacers, which don't conduct electricity. They keep the screens apart to make sure there aren't any false touch signals. When the screen is on, a small voltage is applied across the screen in both horizontal and vertical directions. As soon as you push down on the flexible screen with anything, like your finger or a stylus, it connects the two layers together. This changes the voltage, and a small processor connected to the screen can calculate exactly where you pressed in X and Y coordinates. These resistive touch screens are pretty affordable and durable, so they're used for things like credit card readers and grocery stores where you need to capture touch data of a messy signature over and over again, but they can be a little frustrating to use if you don't push hard enough. Plus, they normally can't understand multiple touches at the same time, so they're no good for two-finger zoom or more complex tasks. That's why these days, most smartphones rely on capacitive touchscreens, where your finger becomes a key part of the electronics. There are different kinds of capacitive touchscreens, and they can vary from device to device. But one basic design is a sheet of glass containing a grid of hair-thin lines of a conductive metal, like indium tin oxide. The grid lines in one direction are called the driving lines, which provide a constant electric current, and the lines in the other direction are called the sensing lines and detect this electric current. At every point where the sensing lines and driving lines cross, there's a specific electrostatic field, which is registered as neutral by the processor in your smartphone or computer. But that all changes when something conductive comes along and touches it, like your finger. See, the human body has a natural capacitance, which means our bodies can conduct electric current and can store electric charge. So when your finger touches the screen, the charge in the screen is drawn around that point, distorting the electrostatic field. The electricity doesn't actually flow through your finger. The electrostatic field feels the effects of your electric charge and redistributes itself accordingly. Even really small changes are detected by the processor, which can then interpret the patterns you're making, whether it's a tap or a slide. Because the lines of the grid are so thin, capacitive touchscreens are super accurate, and some versions can process multiple touches at a time. But they won't work if you have gloves on, because the cloth isn't conductive, unless your gloves have those special fingertips with metal fibers inside. Plus, something like sweat can affect how electricity is conducted across the screen, because it's full of salts. It's all about the materials that can affect the electrostatic field generated inside your screen. So the next time you're texting on a smartphone or scrolling through internet forums on a tablet, just remember, you're actually a part of the electronics that make it work. Thank you for watching this episode of SciShow, brought to you by our patrons on Patreon. If you want to help support the show, you can go to patreon.com/scishow, and don't forget to go to youtube.com/scishow and subscribe.
Like with your Google Glass, cell phone,
Touch screens are everywhere, not just in smartphones, but in...
I take it you don't want to hear that again? Did he talk fast enough? The display quality is determined by two factors: the number of dots and pixels. The quality of the dots in the background are all the pixels, okay? So in 1992, there was a 160 by 293 screen pixel, right? In 2001, there were 256 colors. In 07, we got up to 153,600 pixels. Guess what's happened today? With another technology, we're up to 2 million pixels on your screen. Okay, we're going to talk about semiconductor development. To do that, I've got to change the screen a little bit here. Huh. Semiconductor industry is the one industry, it's the foundation and building blocks of all the technologies we've seen in our phone, right? If we're talking about storage capacity, or the processor speed, or the internet speed, or the camera technology, no matter what we're talking about, it required developments in the semiconductor industry to make this happen. And again, semiconductors are things made of sand. You know, I'll show you that in a minute. Let's take a look at the industry in a little more detail. What is it, right? What's its history? What does it take to make a semiconductor? How do they do it, right? Semiconductors are materials that have the conductive capacity between capacitors. They're non-conductive, or insulators, okay? And don't worry about not understanding that, that's okay. The trend in the 1950s, the discovery and invention of a new electronic semiconductor material and the drastic reduction in the size of electronics devices has moved at a rapid pace. As a result, the speed of electronics have increased at a rapid pace as well. I often tell my classes, I say, gee, how many additions can my iPhone do in a second? And they're somewhere around 3 billion additions a second. Right? I say 2 here, right? The push for smaller devices allows increased functionality in a smaller space. And we started out with the vacuum tubes, and now we're down to nearly a single atom in terms of making a semiconductor. Think about that. Human beings somewhere in this world are working in a manufacturing facility that are able to make something and form something at the atomic level. How small is small? Well, I will go down to from 1 meter is about 3 feet, right? A centimeter is 1/100th of a meter. A millimeter is 1/1000th. A micrometer. A micrometer, just a minute. A micrometer, a micron. Goodness, I can't get it to stop. A micron is 1/1,000,000th of a meter. A nanometer is 1/1000,000th of a meter. 50 microns, it's way up here, is the diameter of a human hair. 40 microns is the lowest level we can see with our human eye, with unaided. A white blood cell is 25 microns. 8 microns is the red blood cell. And a bacteria is 2 microns. And guess what? Our coronavirus is 90 nanometers. And just to give you, whoops, I'm going to skip this one. Oh, there you go, yeah. Again, going through the comparison with some things by the side, I'm going to clear down here to the bottom. Okay, we're now making semiconductors in this range, the size of an oxygen molecule, where I can make images that are created by human beings. What it takes to make semiconductors is, first of all, a lot of money, a lot of space, very clean environment, 7 to 10 times cleaner than an operating room. I don't think you're going to get corona in this space, right? because a very small particle can destroy the device, right? Takes a lot of time to make it. Takes from 1 to, well, it's actually more than 2 months to make the little things that go in your phone. Now I want to talk about the terminology. I'm going to switch gears here a minute. I'm going to end the slideshow. And I'm going to close that screen. Ooh, am I still on? Yes?
Yeah, we're seeing your desktop icons and we see you.
You see
Not
me?
you. We don't see you, but I mean your screen
Yeah, hold on. I'm
in
gonna
the woods.
Oh, you see the woods?
Yep.
Man, how do I get you back on that screen?
I think you have to stop share screen.
Gotcha. You're right. Yes. Okay. I need to demonstrate something to you, right? You. And if you want to change your view so you're in gallery view and see me, I'm sorry, speaker view, right? Here's what you wear to make semiconductors. This isn't getting ready for coronavirus. This is making semiconductors, clear down to booties, right? So if you work in one of these places, and let me show you what that place looks like. Okay, so now I'm in a semiconductor factory, right? And if you look down the aisle here, thousands and thousands of dollars worth of equipment, right? And what they're doing there is they first of all start out with sand. And when they have the sand, they heat it, so it's molten sand, and they start extracting it by going around, starting a little crystal of it, and they start going around. And they withdraw it out of the molten liquid, and it comes out looking like this, right? I realize you can see through it sometimes. Get the idea? And then they take it and they cut it.
We don't see anything.
You don't see any? What are you seeing? Me?
The whole gallery.
I'm seeing it. Oh, that switch the view. Go to the
Switch-
top right and go to the change to speaker
Speaker
view.
Okay.
Okay, no, don't talk though, right? And so this is what you end up with, right? And they take that and they slice it, right? Now that particular cylinder was made in 1980. Since then, they figured out a way to make them bigger, more in diameter. This thing weighs about 10 pounds, right? Sack of potatoes. They figured out a way to make them bigger. And when they slice them, they end up with something that looks like this. And I should flip it over because that one's been processed. So if I flip it over to the other side, actually broke this one, but it's that big, right? And they have them up to 12 inches in diameter. It's that circular, right? So it really is kind of cool that they're able to make those. And then what they do is they go through a process of photographic process, and I can cover a little bit of that later. And then they cut it up into little pieces called chips. So this is called a wafer. And these are called chips. Now they've been taken off the wafer and placed into this little carrier, right? And then we take the chips and we surround them by plastic and put some connectors to it so they can be put on. And I think most of you have heard the term motherboard, right? They put them on a motherboard. And that's how they make the motherboard for your computer, your laptop, and your cell phones. Okay. So there we have the cylinders we talked about. And there's the wafers. It takes 6 to 8 weeks, up to 15 weeks to make to finish one of the wafers. And it goes through a process. And it's kind of like a photographic process, right? Where you apply some chemicals to that wafer. It's nice and shiny. And you apply some chemicals in it. It's called deposition. And then you put a photoresist material. You're going to put an image of something on that wafer, right? And then you go through a lithographic process where you actually photographically put an image on the wafer, right? And then you remove, let's say it's black and white image, and you remove the black, let's say you remove the black and you have the white image left, right? And then where the image is, you implant some stuff, some electronic stuff, okay? And you strip it away, and then you do an ion implant to it to force it into the wafer, into the silicon. And then this process, and then the top layer is stripped away, and you have what remains underneath. And then you go through this process again and again and again, 20 to 40 times before you've built up enough structure to actually make the electronic device you're trying to make. Okay, so we go from wafer, and some people call them chips, other people call them die, right? And they're the cut up portions of the chip or the wafer. The packaging process, you take the silicon wafer, you make chips out of it, and then you put it in a plastic package. Then you place it on a motherboard. Have you ever seen the inside of a computer? It's green in there usually, and there's these chips mounted, the plastic packages. So I just want to give you a short clip about a semiconductor factory, just to give you an idea of what's involved.
This video will give you a quick tour of our Richardson, Texas 300mm analog manufacturing facility. You'll notice there's not a lot of people inside the facility, as the equipment is highly automated. Moving forward, the majority of our incremental analog revenue will continue to be built on 300mm factories like our fab. We'll start at the very first stages of manufacturing process and then switch to our assembly test facilities where we package and test and make the product ready for final shipment. We hope you enjoy the tour.
You are about to enter one of the most technologically advanced manufacturing facilities in the world. Welcome to Texas Instruments Richardson Fabrication Facility, also known as our fab. These amazing facilities deliver advanced semiconductor solutions that are driving advances in automobiles, industrial systems, communications, and more. But the semiconductor chips that TI makes don't start out as the tiny devices you see here. They begin as thin slices of pure silicon. Over time, these silicon wafers have increased in size from just over an inch to the state-of-the-art 300mm wafers produced today. In fact, our fab was the world's first 300mm analog wafer fab. These larger wafers allow TI to build as many as 50,000 chips on a single wafer. This gives TI the capacity to produce billions of integrated circuits each year. A quarter of our fab's 1.1 million square feet is a dedicated clean room space, making it one of the largest clean rooms in the world. On your tour, You're likely to see RFAD team members wearing special clothing that ensures body oils, skin flakes, and lost hairs don't contaminate the massive clean space. Even the airflow in the facility is designed to virtually eliminate all particles in the air. With all the amazing things you'll see here at RFAD, what you won't see is people carrying around heavy containers of silicon wafers. 99% of the wafer movement in this facility is automated, with computer-controlled pods on overhead tracks, making as many as 19,000 pickups and deliveries a day. These pods also protect the wafers by creating a mini environment that is even cleaner than the rest of the fab. It's all part of the intricate process of manufacturing unbelievably tiny technology that packs a powerful punch. Now that you've seen the wafers manufactured, the next and final stage of the process begins. Wafers are shipped to TI's test sites around the world. They are then encased in plastic packages that protect the chip inside and provide electrical connection points so that they can be easily integrated into the intended device. Texas Instruments offers state-of-the-art packaging technologies, from extremely simple to incredibly complex. The first step of the assembly test process is called back grind, which is a process that ensures the finished chips are as thin as possible. Next, each wafer is cut into individual dies or chips. In the die attach process, each chip is placed on a substrate or metal frame, which will be included in the final package. During wire bonding, a material such as copper is used to bond the electrical interconnections between a semiconductor and its packaging. The mold process is where the chip and interconnects are inserted into the familiar epoxy plastic package that protects the chip inside. Next, during symbolization, trim, and form, packages are imprinted with TI's logo and other identifying information and trimmed to their final size. The packaged chips then undergo a final electrical test to ensure that they are performing to their intended specifications, and a visual mechanical inspection to verify that each chip is properly packaged. The packaged chips are then placed onto a special plastic tape and wound onto a reel. This tape and reel delivery is designed to simplify chip placement into their intended devices.
This video will
Ooh. So now let's move on beyond semiconductors. The camera in your device. What's the camera look like? Well, in 2018, 1 trillion pictures were taken with smartphones. The best smartphone camera collects 16 million pixels, and that's little dots with every picture, right? And the camera looks something like this, right? By the way, in comparison to the smartphone taking 16 million pictures or pixels, the human eye has around 120 million light sensing rods. So we have a ways to go till we catch up with the quality of the human vision, okay? And look at this, look at this. There's actually a motor in that camera that's in your phone, right? That controls the focus. Every once in a while, you'll be focusing in on something you're taking a picture of, and it's out of focus, and then it goes into focus. That's the motor working, right? All of our smartphones have two. Now we'll switch to speaker technology from camera technology. Speakers. All of our smartphones have 2 speakers, right? One for your ear and one at the base of the phone that you can use as a speaker, right? The large speaker at the base is the size and weight of a dime. The smaller one is about 1/5 that size, right? Now I could go through a video here and tell you how they did that, but I'm going to skip that one, right? And then we have the battery technology, right? The battery has become 5 times better, even though you have to charge it every day. Your phone does so much more compared to what it did 5 years ago. The batteries we use tomorrow will weigh the same, but will have more energy in them. The target is at least twice the energy. And we're still waiting for a huge breakthrough in battery technology. Speech recognition, right? Just the history here. Audrey from Bell Labs could recognize a single voice speaking numbers. If you remember, you used to be able to say, they would say, what number would you like to call? 7, 3, 5, right? In '62, IBM introduced Shoebox, and they could respond to 16 different words: go, stop, etc. In '70, Carnegie Mellon boosted that to 1,000 words. In 1980, several thousand words, right? From a few hundred to several thousand. And of course, in the 90s, right? Bell came up with a dial-in interactive voice recognition system. And since then, 2001, the systems were 80% accurate. In 2011, Amazon's Alexa and Google Home, we've seen consumers becoming more and more comfortable with talking machines, right? Let's see, it says here, IBM achieved a word error rate. That's how much error do they make? 6.9%. In 2017, Microsoft usurped IBM with a 5.9, and Google is now claiming a 4.9% error rate. The technology to support voice applications is now both relatively inexpensive and powerful. And again, I explained to you earlier how voice recognition works. You know, it has to go from your phone to the computers to a couple of different processes and come back to you. In the future, you will not only be able to write, oh yeah, I made this comment. In the future, you will not only not be able to write cursive, you probably won't even be able to write at all. Fingerprint recognition, right? That's the screen. You touch the screen, and there's a capacitance and ultrasonic, right? Capacitance is what's on your iPhone with that little button at the bottom of your iPhone. And they're working on one where you can touch your screen at a particular place, and it will be able to read your fingerprint. It's called the ultrasonic. That has not happened yet. Facial recognition, right? Facial recognition is a way to recognize the human face through technology, right? It's expected to grow to $7.7 billion by 2022. The process is a picture is taken of your face. The software reads the geometric patterns of your face, and it comes up with a facial signature. That facial signature is a mathematical formula, and it's compared to a database. A determination is made if that is your face, right? All right. All smartphones have an LED, and it's a flashlight as well, right? The smartphone also has a light sensor in it, so that when it's dark, the screen gets not darker, but dimmer. And when you're in the sunlight, it brightens the screen. And when you put your phone to your ear, it determines darkness, and in some cases actually turns off the screen. When you lay your phone face down on a table, it says, oh, I'm in the dark, upside down. I think I'll turn the screen off. So why are your smartphones so magical? It has combined all these advances in technology in one place and has made it available literally at our fingertips. It may seem costly, but when you consider what it can do, it is truly amazing. The amazing smartphone. Now, all that is required is we learn how to use it all. One thing at a time. All right, so there's a picture of an iPhone and an Android. Do I have any questions? I'm done, Ann. Turn on your speaker. Turn on your microphone.
Oh, I've got it on. Oh,
Okay.
Bill, that's an incredible, incredible presentation. My gosh, I'm overwhelmed.
You're
I'd
supposed
like
to
to
be.
share something
Go ahead, Marshall.
quickly. From mid 60s to the mid 70s, I worked at EMR. They were developing micro components.
Yep.
And I was in the lab one day and I noticed like a cup full of these. And I said, what are you doing with those? He said, we're going to throw them away. They failed test. And I said, could I have one? He said, you can have as many as you like. And he said, what are you going to do with it? I said, I'm going to make a tie tack out of it. Now I can show you.
Yeah. Oh, we can't see you. Hold on. We lost your image. Keep talking.
I can
You
see
can
him.
see me.
Marshall, keep talking. So
I'm talking.
There you
There
go.
you go.
Can you see it?
Yeah, it's a little
Yes.
blurry.
Well, it's very small. Let me see if I can get it up closer. No, that's worse. Well, you can see my finger
Right.
in relation. Anyway, this was called an operational amplifier, and they required one or more on a PC board. The guy was very kind
I
to
think it's
give
one
me
of
that.
these.
Whoops, sorry.
It's one of these. If you take
Probably,
one
yes.
of those little
Well,
squares.
that's what I'm leading to with this quick story is the fact that I ran into this. I left in the mid 70s. I ran into the guy in the late 90s and we had a chat. And he said, oh, do you still have that chip that you took? And I said, oh, yeah, I made a tie tack out of it. And he said, well, that's a great idea. He said, but you want to know something's interesting? And I said, what's that? And he said, that very same chip now has 75 amplifiers on it, and it's the same size.
Yep.
So there you go.
All right. well,
Absolutely incredible. Absolutely incredible. Bill,
yes.
fantastic presentation. I
Okay.
think we all learned a lot. I know I did. I never understood what those things that you could see on the motherboard were all about. And at least I know at least where they came from, if nothing more.
That's all. That's all.
That is fantastic. And I'm surprised nobody had any questions, except that I don't know what they could ask. You were very complete. You told us everything. Huey and Bill, thank you both so much for doing this tonight.
You're
and
welcome.
If everybody stays around for just one moment, we're going to find out who has won the $50 Amazon gift certificate. Huh. Just a moment. I've got to go through my magic to find out. Just a second. I'll be right back.
It must be on a chip.
Oh my gosh, that's exactly where I found it. Now I have to scroll through and get my gallery view back, because if the person's not here, well, then we just have to pick somebody else. So I'm looking and I'm looking and I'm looking and I've discovered her. And guess what? Tonight's winner is, drum roll, Nancy DeMarch. Nancy, congratulations. You have won a $50 gift certificate from Amazon. And Sharon Rump is going to get that sent to you in a day or two, I hope. And we are just thrilled that you did this. Would you have a few moments to say a few words? I'm putting you on the spot, but you have to you have to unmute yourself.
Can't figure out how to unmute.
Nancy, there you
She's
go.
speechless.
I want to thank everybody. Can you hear me?
Yes.
That's the first time I think since I joined STUG back in, well, it was STUG then, back in 2000, maybe 1999. It was the first time I think I won anything, but it was lovely.
And it was worth waiting around for, right?
Right.
Well, congratulations. We're thrilled that you did. And we were so thrilled that all of you came tonight. As a matter of fact, there are 64 of you still here. I think that's wonderful. Bless you for staying with us throughout the presentation. Bless you, Bill. Bless you, Huey. Bless you, everybody. Thank you again. And we'll see you in class, right? Is there anybody else that would like to say anything before we close the meeting?
Yes, I have here an IBM card with 80 columns from the olden days. Actually, it's an IBM STUG certificate for your enjoyment.
Did you say stock certificate?
No.
Yes, when I was issued some stock when I worked for IBM. This was the stock certificate.
Oh, for heaven's sake.
He's holding it up.
And somewheres around here, I have an 8-inch floppy disk. Not a 5-inch floppy disk, but an 8-inch floppy disk. So things have certainly gotten smaller and faster over the years.
And what are we going to do with all of these things, devices that we have collected over the years?
We talk about them at STUG meetings.
And if they're laptops, we donate them to Refurb.
Right.
Absolutely.
Right.
Very good.
And
Right.
and I still have a slide rule.
Oh, no.
Keep it. It's probably worth millions.
It's going to be an antique. It'll have value at some point.
As long as somebody knows how to use it.
Yeah, do
Don't
you-
forget that.
Okay, well,
Yes,
is there,
may I mention, I have a slide rule that I picked out of a trash can when I worked for the Federal Reserve Board in Washington. And I asked the manufacturer one day if he had any idea how old he was. He said it was made between 1910 and 1915.
Oh,
It must have been at the Fed at the very beginning. So I donated it to the Federal Reserve Board's museum in Washington.
probably a good place.
Actually, I can do one better. I have an abacus.
Ah,
On that note, I'm going to stop the recording. I did remember to start the recording right at the beginning of Bill's presentation, so it will be up on the STUG channel. I'm going to stop the recording.